All right, and welcome back, folks. So, last time we finished talking about integrating factors and a little bit of subtleties that you might incur when employing our general solution. And we actually came across our first differential equation that actually didn't have a solution. So, it looks like anything's possible here, even in the simplest of cases. And let's go ahead and keep going on this foray into first order equations by dropping the linearity condition for the moment. Let's say that we don't have a linear equation like we did back here at the beginning of section 2.1. Let's say that we still have a first order equation though, and that means that we can write this guy. Oh, that's in red. No, I would like, oh, no, come back. I would like the white equation there. There we go. Or not the white equation, I want the white pen because it's easiest to see on this background. That means that we would have a derivative dy dx equals f of x and y. So there is a rate function here on the right-hand side, even though I have used x instead of t. Shh, don't tell anyone. But the idea is that if I am able to write this guy in a particular form, if I can write this as, let's say it would be h of x over g of y, and you'll see why I'm doing that in a moment. If we separate this equation, then we would wind up seeing that we can put the y's on the left-hand side and keep the x's to the right, at which point we can integrate. But that's the whole point here, is that we want to have equations or differential equations that have this form, and when they do, these are called separable equations. And these are among the quickest differential equations to solve. And I do say solve very, very carefully. Because remember, when we're talking about solving differential equations in general, our three goals were about existence, uniqueness, and the third one was on computability. How practical it is to come up with these solutions explicitly, or if we have to appeal to numerical equipment. And this very well is the case for many a separable differential equation. And let me illustrate this with a couple of examples. So let's say that we wanted to find the general solution of this differential equation, which is certainly nonlinear because of this y square component, among other noteworthy features. This is definitely not a linear equation, which means we can't use our machinery from the previous section. But we notice very quickly that we can separate this guy into two pieces. We can separate the y's from the x's. And when we do, we can integrate both sides of this equation, and we wind up with y minus a third y cubed equals 1/3 x cubed plus a constant. Remember, I'm consolidating my integration constants on one side of the equation, so I don't have multiple constants floating around. But notice what happens in this equation. I can't actually solve this for y explicitly. Well, you might argue that I could if I used, I think it's Cardano's equation or Cardano's formula for the cubic, but it's really, really messy, and the point is that this particular equation is actually really, really nice by itself. I don't need to solve for y as a function of x in order for this to be useful. As it turns out, I can go ahead and start plotting these guys, and if we have multivariable calculus experience, if we have multivariable calculus experience, if I set f of x and y equal to y minus 1/3 x cubed minus 1/3 x cubed, then we see that my solutions to this differential equation are exactly the level sets of this function. And I can actually see these level sets, and here's one of them for when c is equal to 0. So this is the graph of a solution, but the solution isn't actually a function when I think of y supposedly as a function of x. This blue curve certainly doesn't pass our vertical line test, right? There are several, there's an entire interval of locations where this blue curve is not a function of x. But what I can do is split up the solution domain. Right? So if I were to think about this as a function, then what I would have to do is think about these branches independently of one another. Right? I would have to look at this and say, okay, up until this point, so if I start up at x equals negative infinity, y equals plus infinity, and then come down along this blue curve, I can do that until I get to this point where I'm perfectly vertical, and then I start to come back. I start to double back along the blue curve. And that is where I lose this function property. But I do have a function up until that point, and that's, whoa. And that's what I have written down here, is that my solution domain actually does extend from minus infinity to D, whatever that location might be, on the top branch. And very similarly, I have a bottom branch down here, whose solution domain starts at minus D and goes up to positive infinity. And there is still this branch in the middle that constitutes its own function, its own solution to the differential equation. But the point is that the solution domain here is actually very, very specific. And we can't actually see that in the differential equation itself unless we look at where this guy doesn't make any sense, where he fails to be true, or to be something that we can recognize. Or sorry, where he fails to have a derivative. And in this case, this is where I'm not allowed to let y squared equal 1, and that would happen at plus or minus 1 in y. So I've highlighted exactly these lines right here to show you this is exactly where my solution domain gets cut off. That it's actually entirely in terms of y here, where I start to lose out on the function property of a solution, or where a solution is no longer a function. And that's that is a subtlety to these separation of variables type solutions, where you do need to be very careful about how you represent the solution. If you do this analytically, you have to take into account a solution domain. But if you do this graphically, then you wind up with a graph that gives you near complete information about your solution, especially if you have an initial condition that you can employ to tell you exactly which level set you're using. So that is very, very tricky, especially if you're thinking about this as y as a function of x. But there's actually nothing stopping us from actually solving for x as a function of y in this equation. So we very well could do that and say that'd be 3y minus 1/3 y cubed minus, I think it'll be a 3c, yeah. And that'll be x cubed. So if I take the cube root of this, then I now have a solution x as a function of y. And that's not too hard to see. If you turn your head sideways for this picture, you can actually see that, sure, this passes not the vertical line test, but the horizontal line test. And there's no problem in my solution domain at this point. So it all depends on a perspective here. It all depends on whether or not you're able to solve for your solution explicitly. So in the same vein as this previous example, let's talk about what happens if we employ an initial condition. So let's do this. dy, so a new example, dy dx is 3x squared plus 4x plus 2 over twice y minus 1. And I'll give it the initial condition y of 0 equals minus 1. Okay. Now, again, let's go ahead and separate variables. So this will be, which one do I want to use? Yeah, I'll put twice y minus 1 dy equals 3x squared plus 4x plus 2 dx. I can integrate both sides, no problem. This will wind up giving me y squared minus 2y. And then on the right side, x cubed plus 2x squared plus 2x plus a constant. And I can go ahead and use my implicit equation here to tell me what the integration constant is going to have to be. So specifically, y is going to have to be a minus 1, and x is 0. So many zeros. I love plugging in zeros. There we go. So 1 plus 2. So C would have to be 3 in this case. So then my explicit or implicit solution would have to be this equation here. And this is just as good as an explicit solution where I'm solving for one of the two variables. But you are still going to have to worry about what your solution domain looks like. Figure out what branch of the function you want to use if you're going to go ahead and use this as a function where one variable is a function of the other. But it still behooves you to know exactly what the graph of this guy looks like, so you can go ahead and throw this into a numerical plotter. And Desmos is actually a great open source thing that you can use, or freely available source that you can use to plot such an equation. And in the notes here, I say there's actually a nifty little trick you can do to show that this equation actually can be solved for y. And I'll actually leave this to my viewers here. Comment down below if you can see exactly how to take this guy and write it as a function of x. And you'll wind up with two branches, two different solutions here. So let me know what you think down in the comments. We'll talk about it. And a few ending remarks here. We have talked about separable equations before, and I didn't talk about them in a terribly great amount of detail because there actually is a fair bit of subtlety to them, and I wanted to talk about it here. Not all first-order equations can be put into this form, into this rate function form. But when you can, there is some simplicity in figuring out what long-term behaviors of your solutions look like. And the equilibrium solutions are exactly those long-term solutions that we'd like to find. This is what happens when you set your rate function equal to 0. So I'm looking at the remark here and looking at the first comment. And we can see that if we set this derivative equal to 0, then the only way that we're going to get this to be 0 for all x is if the numerator goes away, and that only happens when y is equal to the constant 3 function for that particular example. But that tells you that you know exactly what your long-term behavior looks like. You know what your equilibrium solutions look like. Recall from Calc 3, multivariable calc. And if you haven't had it, that's okay, but bear with me here. The idea is that you can think about your solutions in this implicit form as potentially being parameterized as a curve. So you parameterize a curve in the plane, and you could do so as a pair of functions that depend on the same variable. So case in point, this would be something like the unit circle being parameterized as cosine of t by sine of t, right? So you would actually have a nice oriented curve in the plane, right? And it's parameterized by this angle that you make with the positive x-axis. But I digress. That if you think about this solution as being a parameterized curve, then the slope, this dy dx, can actually be thought of as the ratio between these two derivatives, right? It's the slope of your velocity curve. If I think about x prime of t, which is x prime by y prime, then this derivative here is actually just the ratio of the vector, or the slope of the vector here. And thinking about this in terms of our parameterized, in terms of our rate function, if we had two functions here, say f of x and y on top and g of x and y down below, then this is really just telling us more geometric information about our solutions. And it tells us that our derivatives have to, the derivatives of this velocity curve, or the velocity vector, have to actually satisfy their own differential equation to begin with. So dx dt would have to be a function g of x and y, and dy dt would have to be f of x and y. So you could actually think about these guys as solutions to a system of ODEs. And you wind up with more geometric information about the curve than you do if you just think about them in terms of this algebraic manipulation. So I'm a fan of geometric arguments. I like being able to see what these guys are doing. So finally, I will say that in the above examples, we did have a case where we could create explicit solutions from implicit solutions, but this is almost always impossible to accomplish in the general case, right? And this is like every example that we've done here, we actually can solve for some variable explicitly, but this is definitely not going to be the case moving forward. It's going to be impossible to do this in general. Let's say that I had e to the y plus y is equal to e to the x plus c as my implicit formula. There's no way for me to solve this equation for either y or x as a function of x or y, respectively. Did I get that right? Yeah. Then the point is that we would be able to come up with solutions to our differential equations, but they would be in implicit form, and the best we can do is give some sort of geometric representation of them, right? And this would be the best algebraic expression that we could give to tell you what solutions have to look like. So again, solutions can have algebraic interpretations and solutions can have geometric interpretations. And it's very, very obvious that you get this interchange between the two representations when you look at separable equations. So I think that's where I would like to leave this conversation, because we need to start moving. Like it's important that we talk about the theory, but we do need to mix in some context. We do need to remind ourselves what we are doing this for. Like, why are we studying differential equations? Yeah, they're just plain awesome, but there also needs to be some sort of context. And these differential equations are mathematical models. And in the next video, I'll tell you a little bit about how the modeling process works and how you devise a differential equation to study a physical phenomenon. And I think this is this is one of my favorite lectures of this series. I really enjoy